Hello everyone, and welcome back to the series of lectures focused on the main spectroscopic techniques used in the determination of the structure of organic molecules. So far, I have mainly concentrated on the description of X-ray crystallography and mass spectrometry, which are powerful tools for determining the shape and weight of organic compounds. In this lecture, my aim will be to give you a general introduction to the most important physico-chemical technique used to describe the structure of organic molecules. I am speaking about nuclear magnetic resonance spectroscopy, commonly abbreviated as NMR. Nuclear magnetic resonance, NMR, allows us to detect atomic nuclei and say what sort of environment they are in within the molecule. In a molecule such as propanol, the hydrogen atom of the hydroxyl group is clearly different from the hydrogen atoms of its carbon skeleton. It can be displaced by sodium metal, for example. Proton NMR can easily distinguish between these two sorts of hydrogens by detecting the environment the hydrogen's nucleus finds itself in. Moreover, NMR can also distinguish between all the other different sorts of hydrogen atoms present. Likewise, carbon NMR can easily distinguish between the three different carbon atoms in the molecule of propanol. NMR is extremely versatile. It can even scan living human brains, but the principle is still the same, being able to detect nuclei, and hence atoms, in different environments. When NMR is used medically, it is usually called magnetic resonance imaging, MRI, for fear of alarming patients wary of all things nuclear. Imagine for a moment that we were able to switch off the Earth's magnetic field. Navigation would be made much harder since all compasses would be useless, with their needles pointing randomly in any direction. However, as soon as we switched the magnetic field back on, they would all point north, their lowest energy state. Now if we wanted to force a needle to point south, we would have to use up energy and, of course, as soon as we let go, the needle would return to its lowest energy state, pointing north. In a similar way, some atomic nuclei act like tiny compass needles when placed in a magnetic field and have different energy levels according to the direction in which they are pointing. I will explain how a nucleus can point somewhere in a moment. A real compass needle can rotate through 360 degrees and has an essentially infinite number of different energy levels, all higher in energy than the ground state pointing north. Fortunately, things are simpler with an atomic nucleus. Its energy levels are quantized, just like the energy levels of an electron, and it can adopt only certain specific energy levels. The atomic nucleus is like a compass which points, say, only north or south, and nothing in between. Just as a compass needle has to be made of a magnetic material to feel the effect of the Earth's magnetism, so it is that only certain nuclei are magnetic. Many, including normal carbon-12, do not interact with a magnetic field at all and cannot be observed in an NMR machine. But the minor carbon isotope, carbon-13, does display magnetic properties, as does hydrogen-1 or protium, the most abundant atomic nucleus on Earth. When a carbon-13 or protium atom finds itself in a magnetic field, it has two available energy states. It can either align itself with the field, which would be the lowest energy state, or against the field, which is higher in energy. The property of a nucleus that allows magnetic interactions, or in other words, the property possessed by carbon-13 and hydrogen-1 but not by carbon-12, is called spin. If you conceive of a carbon-13 and hydrogen-1 nucleus spinning, you can see how the nucleus can point in one direction. It is the axis of the spin that is aligned with, or against the field. Let us return to the compass for a moment. If you want to move a compass needle away from pointing north, you must push it and expend energy as you do so. If you put the compass next to a bar magnet, the attraction towards the magnet is much greater than the attraction towards the North Pole, and the needle now will point at the magnet. You also must push much harder to move the needle from the magnet. Exactly how hard it is to turn the compass needle depends on how strong the magnetic field is and how well it is magnetized. If it is only weakly magnetized, it is much easier to turn it round, and if it is not magnetized at all, it is free to rotate. Likewise, for a nucleus in a magnetic field, the difference in energy between the nuclear spin aligned with and against the applied field depends on how strong the magnetic field is in the magnetic properties of the nucleus itself. The stronger the magnetic field, the greater the energy difference between the two alignments of the nucleus. Now there is an unfortunate thing about NMR. The energy difference between the nuclear spin being aligned with the magnetic field and against it is exceedingly small. So small that we need an extraordinarily strong magnetic field to see any difference at all. This picture shows a typical NMR instrument. The fat cylinder is a supercooled magnet. The device hanging over it is an automatic sample changer, and the console in the foreground controls the machine. NMR machines contain very strong electromagnets. The Earth's magnetic field has a field strength of between 30 and 60 microtesla. A typical magnet used in an NMR machine has a field strength of between 2 and 10 Tesla, some 10 raised to the power of 5 times stronger than the Earth's field. These magnets are dangerous, and no metal objects must be taken into the rooms where they are. There are many stories about unwitting workers whose metal toolboxes have become firmly attached to NMR magnets. Even with the immensely powerful magnets used, the energy difference is still so small that the nuclei only have a very small preference for the lower energy state. Fortunately, we can just detect this small preference. A hydrogen-1 or carbon-13 nucleus in a magnetic field can have 2 energy levels, and energy is needed to flip the nucleus from the more stable state to the less stable state. But since the amount of energy needed is so small, it can be provided by low-energy electromagnetic radiation of radio wave frequency. Radio waves flip the nucleus from the lower energy state to the higher state. Turn off the radio pulse and the nucleus return to the lower energy state. When it does so, the energy comes out again. And this, a tiny pulse of radio frequency electromagnetic radiation, is what we detect. We can now sum up how an NMR machine works. The sample of the unknown compound is dissolved in a suitable solvent, placed in a narrow tube, and put inside a very strong electromagnet. To even out imperfections in the sample, the tube is spun very fast by a stream of air. Inside the magnetic field, any atomic nuclei with a nuclear spin now possesses different energy levels, the exact number of different energy levels depending on the value of the nuclear spin. For proton and carbon NMR, there are 2 energy levels. Inside the NMR machine, the sample is irradiated with a short pulse of radio frequency energy. This disturbs the equilibrium balance between the 2 energy levels. Some nuclei absorb the energy and are promoted to a higher energy level. When the pulse finishes, the radiation given out as the nuclei fall back down to the lower energy level is detected using what is basically a sophisticated radio receiver. Finally, after lots of computation, the results are displayed in the form of number of absorptions against frequency. Here is an example, which we shall return to in more detail later. In the spectrum you see here, each peak represents a different kind of carbon atom. Each one absorbs energy or resonates at a different frequency. But why should carbon atoms be different? I have told you 2 factors that affect the energy difference, and therefore the frequency. These were the magnetic field strength and what sort of nucleus is being studied. So, you might expect all carbon nuclei to resonate at one particular frequency and all protons to resonate at one, but different frequency. But as you can see on this spectrum, they do not. The variation in frequency for different carbon atoms must mean that the energy jump from nucleus aligned with to nucleus aligned against the applied magnetic field must be different for each type of carbon atom. The reason is that the carbon-13 nuclei in question experience a magnetic field that is not quite the same as the magnetic field that we apply. Each nucleus is surrounded by electrons, and in a magnetic field these will set up a tiny electric current. This current will set up its own magnetic field, rather like the magnetic field set up by the electrons of an electric current moving through a coil of wire, which will oppose the magnetic field that we apply. The electrons are said to shield the nucleus from the external magnetic field. If the electron distribution varies from carbon atom to carbon atom, so does the local magnetic field experienced by its nucleus, and so does the corresponding resonating frequency. This variation in frequency is known as the chemical shift. Its symbol is the Greek letter delta. As an example, consider ethanol. The red carbon attached to the OH group will have a smaller share of the electrons around it compared to the green carbon, since the oxygen atom is more electronegative and pulls electrons towards it, away from the red carbon atom. The magnetic field that the red carbon nucleus feels will therefore be slightly greater than that felt by the green carbon, which has a greater share of the electrons. Since the red carbon is less shielded from the applied external magnetic field, we can call it deshielded. As the carbon attached to the oxygen feels a stronger magnetic field, there will be a greater energy difference between the two alignments of its nucleus. The greater the energy difference, the higher the resonant frequency, as energy is proportional to the frequency. So, for ethanol, we would expect the red carbon, with the OH group attached, to resonate at a higher frequency than the green carbon, and indeed this is exactly what the carbon NMR spectrum shows. The peaks at 77 ppm, shaded brown, are those of the usual solvent, deuterated chloroform, and can be ignored for the moment. I will explain them in the module devoted to further details of proton NMR spectroscopy. When you look at a real NMR spectrum, you will see that the scale does not appear to be in magnetic field units, nor in frequency, nor yet even energy units, but in parts per million ppm. There is a very good reason for this. The exact frequency at which the nucleus resonates depends on the external applied magnetic field. This means that if the sample is run on a machine with a different magnetic field, it will resonate at a different frequency. It would make life very difficult if we could not say exactly where our signal was, so we say how far it is from some reference sample, as a fraction of the operating frequency of the machine. We know that all protons resonate at approximately the same frequency in a given magnetic field, and that the exact frequency depends on what sort of chemical environment it is in, which in turn depends on its electrons. This approximate frequency is the operating frequency of the machine and simply depends on the strength of the magnet. The stronger the magnet, the larger the operating frequency. The precise value of the operating frequency is simply the frequency at which a standard reference sample resonates. In everyday use, rather than referring to the magnet strength in Tesla, chemists usually refer to its operating frequency. A 9.4 Tesla NMR machine is referred to as a 400 MHz spectrometer, since that is the frequency in this strength field at which the protons in the reference sample resonate. The compound we use as a reference sample is usually tetramethylsilane, TMS. This is a silane with each of the hydrogen atoms replaced by methyl groups. The 4 carbon atoms attached to silicon are all equivalent, and because silicon is more electropositive than carbon, they are fairly electron-rich or shielded. Silicon and oxygen have opposite effects on an adjacent carbon atom. Electropositive silicon shields, electronegative oxygen deshields. Shielded methyl groups mean that they resonate at a frequency a little less than that of most organic compounds. This is useful because it means our reference sample is not right in the middle of our spectrum. The chemical shift, delta, in parts per million of a given nucleus in our sample is defined in terms of the resonance frequency by this equation. No matter what the operating frequency of the NMR machine, the signals in a given sample will always occur at the same chemical shifts. In ethanol, the carbon attached to the OH resonates at 58 ppm, whilst the carbon of the methyl group resonates at 18 ppm. Notice that by definition TMS itself resonates at 0 ppm. The carbon nuclei in most organic compounds resonate at greater chemical shifts, normally between 0 and 200 ppm. Now, let's return to the sample spectrum of lactic acid, and you can see the features we have discussed. This is a 100 MHz spectrum. The horizontal axis is frequency, but usually quoted in ppm of the magnet's field, so each unit is 1 ppm of 100 MHz. We can tell immediately from the 3 peaks at 177, 66, and 20 ppm that there are 3 different types of carbon atom in the molecule. Again, ignore the brown solvent peaks at 77 ppm, they're of no interest to us now. You also need not worry about the fact that the signals have different intensities. This is a consequence of the way the spectrum was recorded, and in carbon NMR spectra signal intensity is usually of no consequence. The strategies used to spot the identity of these signals will be described in the following lecture. To sum it up, in this lecture, we learned about the main principles of how nuclear magnetic resonance spectroscopy works. You have seen how the electronic environment around an NMR-active nucleus affects the region where the signal corresponding to that nucleus appears. We also learned about the internal standard tetramethylsilane used to standardize the work of various NMR machines operating under different frequencies. The following lecture will focus more on specific examples of organic molecules and their NMR spectra. You will be introduced to proton and carbon NMR spectroscopies. Your attention and participation are greatly appreciated. Hello everyone, and welcome to the second lecture designed to introduce you to the main concepts in nuclear magnetic resonance spectroscopy. You should now know about the main principles of how the NMR machine works. You were also introduced to the main concepts allowing the rational interpretation of NMR spectra using the instance of carbon NMR of ethanol. Here, our main focus will be on the exploitation of the ideas learned in the previous lecture for the determination of the structure of simple organic molecules by carbon and proton NMR spectroscopies. The last spectrum I described in the previous lecture was the carbon NMR of lactic acid, also known as 2-hydroxypropanoic acid. Every time you move your fingers, you produce some lactic acid from glucose in the muscles of your arm. It is the breakdown product of glucose when you engage in anaerobic exercise. Each of lactic acid's carbon atoms gives a peak in a different region of the spectrum. But hang on one moment, you may say, don't we only see signals for carbon-13 nuclei and not carbon-12, which make up most of the carbon atoms in any normal sample of lactic acid? The answer is yes, and indeed only about 1.1% of the carbon atoms in any sample are visible by carbon NMR. But since those carbon-13 atoms will be distributed randomly through the sample, this does not affect any arguments about the spectrum's appearance. What it does mean, however, is that carbon NMR is not as sensitive as proton NMR, where essentially all of the hydrogen atoms in the sample will be visible. In fact, the low abundance of carbon-13 in natural carbon makes carbon spectra simpler than they would otherwise be. Accordingly, all carbon spectra can be divided into 4 major regions. These include saturated carbon atoms, 0 to 50 ppm, saturated carbon atoms next to oxygen, 50 to 100 ppm, unsaturated carbon atoms, 100 to 150 ppm, and unsaturated carbon atoms next to oxygen, like carbonyl groups, 150 to about 200 ppm. The chemical shift scale runs to the left from 0, where TMS resonates, backwards from the usual style. Chemical shift values around 0 are obviously small but are confusingly called high field, because this is the high magnetic field end of the scale. I suggest you say large or small chemical shift and large or small delta, but high or low field to avoid confusion. Alternatively, use upfield for high-frequency signals and downfield for low-frequency signals. Another helpful description I have already used is shielding. Each carbon nucleus is surrounded by electrons that shield the nucleus from the applied field. Simple saturated carbon nuclei are the most shielded. They have small chemical shifts between 0 and 50 ppm and resonate at high field. One electronegative oxygen atom moves the chemical shift downfield into the 50 to 100 ppm region. Unsaturated carbon atoms experience even less shielding between 100 and 150 ppm due to how electrons are distributed around the nucleus. You should know that unsaturated carbon atoms are more deshielded than saturated ones because a pi bond has a nodal plane, or a plane with no electron density at the nucleus. Electrons in pi bonds are less efficient at shielding the nucleus than electrons in sigma bonds. If unsaturated carbon atoms are also bonded to oxygen, then the nucleus is even more deshielded and moves to the largest chemical shifts around 200 ppm. So, onto some real carbon NMR spectra. Our very first compound, hexanedioic acid, has the simple NMR spectrum shown here. The first question is, why only 3 peaks for 6 carbon atoms? This is because of the symmetry of the molecule. The 2 carboxylic acids are identical and give 1 peak at 174 ppm. For the same reason, C2 and C5 are identical, and C3 and C4 are identical. These are all in the saturated region, but the carbons next to the electron-withdrawing carboxyl group will be more deshielded than the others. So we assign C2 and C5 to the peak at 33 ppm and C3 and C4 to the peak at 24 ppm. This spectrum was run in a different solvent, dimethyl sulfoxide, hence the brown solvent peaks are in a different region and have a different form. Again, we will deal with this later. Heptantuon is the bee pheromone mentioned earlier. It has no symmetry, so all its 7 carbon atoms are different. The carbonyl group is easy to identify at 208 ppm, but the rest are more difficult. The 2 carbon atoms next to the carbonyl group come at lowest field, while C7 is at the highest field at 13 ppm. It is important that there is the right number of signals at about the right chemical shift. If that is so, we are not worried if we cannot assign each frequency to a precise carbon atom, such as atoms 4, 5, and 6. As I said before, do not be concerned with the intensities of the peaks in carbon NMR. Here is the carbon NMR spectrum of butylated hydroxytoluene, BHT, which is a well-known antioxidant. The first surprise in its NMR spectrum is that there are only 7 signals for the 15 carbon atoms. There is obviously a lot of symmetry. In fact, the molecule has a plane of symmetry vertically as it is drawn here, and the colored blobs indicate pairs or groups of carbons related to each other by symmetry, which therefore give only one signal. The very strong signal at 30 ppm belongs to the 6 identical methyl groups on the tert-butyl groups, and the other 2 signals in the 0 to 50 ppm range are the methyl group at C4 and the brown central carbons of the tert-butyl groups. In the aromatic region, there are only 4 signals as the 2 halves of the molecule are the same. As with the last example, we are not concerned with exactly which is which, we just check that there are the right number of signals with the right chemical shifts. Paracetamol is a familiar painkiller with a simple structure. It also is a phenol, but in addition it carries an amide substituent on the benzene ring. Its NMR spectrum contains 1 saturated carbon atom at 24 ppm corresponding to the methyl group of the amide side chain, 1 carbonyl group at 168 ppm, and 4 other peaks at 115, 122, 132, and 153 ppm. These are the carbons of the benzene ring. The 2 halves of the benzene ring must be the same, so we have only 1 signal for each pair of carbons colored red and green. This also tells us that the amide substituent does not really lie just to one side as shown here, but rotates rapidly, meaning that on average the 2 sides of the ring are indistinguishable, as in the previous example. You may ask, why is one of these aromatic peaks in the carbonyl group region at 153 ppm? Well, this must be C4 as it is bonded to oxygen. A reminder that carbonyl groups are not the only unsaturated carbon atoms bonded to oxygen. Proton NMR spectra are recorded in the same way as carbon NMR spectra. Radio waves are used to study the energy level differences of nuclei, but this time they are hydrogen-1 and not carbon-13 nuclei. Like carbon-13, hydrogen-1 nuclei have a nuclear spin of 1/2, and so have 2 energy levels. They can be aligned either with or against the applied magnetic field. Here, as an example, is the proton NMR spectrum of acetic acid. The carbon NMR spectrum is shown below. Proton NMR spectra have many similarities with carbon NMR spectra. The scale runs from right to left, and the 0 point is given by the same reference compound. Though it is the proton resonance of tetramethylsilane rather than the carbon resonance that defines the 0 point. However, as you immediately see in the spectrum above, the scale is much smaller, ranging over only about 10 ppm instead of the 200 ppm needed for carbon. This makes perfect sense. The variation in the chemical shift is a measure of the shielding of the nucleus by the electrons around it. There is inevitably less change possible in the distribution of 2 electrons around a hydrogen nucleus than in that of the 8 valence electrons around a carbon nucleus. Nonetheless, the acetic acid spectrum above shows you that, just as you would expect, the hydrogen atom of the carboxyl group, directly attached to an oxygen atom, is more deshielded than the hydrogen atoms of acetic acid's methyl group. We can also divide up the proton NMR spectrum into regions that parallel the regions of the carbon NMR spectrum. Hydrogen atoms bonded to saturated carbon atoms appear in the right-hand, more shielded region of the spectrum, while those bonded to unsaturated carbon atoms, alkenes, arones, or carbonyl groups, appear in the left-hand, less shielded region between 10 and 5 ppm. As with the carbon NMR spectrum, nearby oxygen atoms withdraw electron density and make the signals appear towards the left-hand end of each of these regions. You can see exactly how proton NMR signals fall into these regions in the following collection of spectra. The first 2 spectra each contain only one peak because every proton in benzene and in cyclohexane is identical. In benzene, the peak is at 7.5 ppm, where we expect a proton attached to an unsaturated carbon atom to lie, while in cyclohexane it is at 1.35 ppm because all the cyclohexane protons are attached to saturated carbon atoms. Again, to help comparisons, I have also included the carbon NMR spectra of benzene and cyclohexane. For benzene, the signal falls in the unsaturated carbon region at 129 ppm, while for cyclohexane it is in the saturated carbon region at 27 ppm. Tert-butyl methyl ether is a solvent and fuel additive whose proton NMR spectrum illustrates the effect of a nearby oxygen atom. The large peak at 1.1 ppm comes from the 9 hydrogen atoms making up 3 identical methyl groups of the tert-butyl part of the molecule, while the 3 hydrogen atoms of the methyl part of the ether are at 3.15 ppm. These 3 hydrogen atoms are all bonded directly to a carbon atom, which itself is bonded to oxygen, whose electronegativity attracts their electrons, deshielding the hydrogen nuclei and shifting them to larger chemical shift. The plane of symmetry I noted in the carbon NMR spectrum of BHT means that the proton NMR spectrum of the related fuel additive, Topanol 354, is relatively simple, considering it has 26 hydrogen atoms. The large peak between 2 and 1 ppm corresponds to the 18 protons of the tert-butyl groups. Additionally, at around 4 ppm, the signal appears for the protons from the methoxy group, while the proton directly attached to the oxygen of the hydroxyl group shows up as a broad signal between 6 and 5 ppm. The symmetry in the molecule ensures that the 2 protons in the ring are identical, and the signal around 7 ppm corresponds to the aromatic hydrogens, as indicated in green. Proton NMR exhibits many more features, which we will set aside for the moment. It is no exaggeration to say that, in general, proton NMR is more critical for the routine determination of structure than all the other methods combined. We will revisit proton NMR in more detail in a separate module. To illustrate the power of NMR, consider these 3 alcohols with the formula C4H10O, each exhibiting a distinct carbon NMR spectrum. The peaks from the spectra are presented in the table below. In each alcohol, a saturated carbon atom adjacent to oxygen appears in the typical region for saturated carbon atoms next to electron-withdrawing groups. Next, there are carbons located 1 atom away from oxygen, situated in the 0 to 50 ppm region, with their positions at the low field end, due to deshielding by the nearby oxygen atom. 2 of the alcohols have carbons separated from the oxygen atom by 2 carbon atoms. They are only slightly shielded and appear around 20 ppm. Only N-butanol, however, has a more remote carbon located at 15.2 ppm. Here, the number and chemical shift of the signals distinctly identify the isomer structures from each other. A common situation chemists find themselves in is that they have some idea about a molecular formula from high-resolution mass spectrometry and need to match a structure to NMR data. Here is an example. The formula, C3H6O, is represented by 7 reasonable structures. The 3-carbon NMR spectra shown here represent 3 of these compounds. The challenge is to identify which 3. Simple symmetry can distinguish structures A, C, and E from the rest, as these 3 have only 2 types of carbon atom. The 2 carbonyl compounds, D and E, will have one peak in the 150 to 200 ppm region, but compound E has 2 different saturated carbon atoms while compound E has only one. The 2 alkenes, F and G, both have 2 unsaturated carbon atoms that should appear between 100 and 200 ppm. But in ether G, one of them is connected to oxygen. You would expect it therefore to be deshielded and to appear between 150 and 200 ppm. The 3 saturated compounds, A, B, and C, present the greatest problem. The epoxide B has 2 different carbon atoms next to oxygen and 1 normal saturated carbon atom. The remaining 2 should both have 1 signal in the 0 to 50 ppm region and 1 in the 50 to 100 ppm region, and only the more powerful techniques of proton NMR and, to a certain extent, infrared spectroscopy will distinguish them reliably. The only carbonyl compound with 2 identical carbons is acetone, so spectrum 1 must be that one. Notice the very low field signal at 206 ppm, typical of a simple ketone carbonyl carbon atom. Spectrum 2 has 2 unsaturated carbons and a saturated carbon next to oxygen, so it must be F or G. In fact, it has to be compound F, as both unsaturated carbons are similar, and neither is next to oxygen. Remember, unsaturated carbon next to oxygen appears at around 150 ppm. This leaves spectrum 3, which appears to have no carbon atoms next to oxygen, as all chemical shifts are less than 50 ppm. However, the 2 signals at 48 and 48.2 ppm are suspiciously close to the arbitrary 50 ppm borderline. They are, of course, both next to oxygen, and this must be compound B. To summarize, in this lecture, we learned about the regions where typical functional groups appear in carbon and proton NMR spectra. Using specific examples, you saw how this information can be used for the determination of the structure of organic molecules. The following lecture will introduce the basic principles of infrared spectroscopy and its use in identifying common functional groups in organic compounds. Thank you for your attention. Greetings to all, and a warm welcome to the module devoted to proton nuclear magnetic resonance spectroscopy with applications to organic chemistry. In a separate module, I introduced nuclear magnetic resonance, NMR, as part of a 3-pronged attack on the problem of determining molecular structure. I showed that mass spectrometry weighs the molecules, infrared spectroscopy tells us about functional groups, and carbon and proton NMRs tell us about the hydrocarbon skeleton. I concentrated on how NMR works, particularly on carbon NMR, because it is simpler. I was forced to admit that I was leaving the details of the most important technique of all until a later module, as it is more complicated than carbon NMR. This is the module where we must tackle those complications. We are going to learn more details about the most important regions in proton NMR spectroscopy. You will see similarities and differences between carbon and proton NMR, and you will be introduced to integration, enabling quantification of the data from proton NMR spectroscopy. Finally, you will learn how protons in a molecule interact with each other and how this can be used to find the structure of an unknown molecule. Hopefully, after this module, you will see all the beauty and power of proton NMR. The difficulties are worth mastering, for this is the chemist's primary weapon in the battle to solve unknown structures. Proton NMR spectra are recorded in the same way as carbon NMR spectra. Radio waves are used to study the energy level differences of nuclei in a magnetic field, but this time they are hydrogen-1 and not carbon-13 nuclei. Hydrogen nuclei in a magnetic field have 2 energy levels. They can be aligned either with or against the applied magnetic field. Here's the proton NMR spectrum of acetic acid, which you first saw in the introductory module on structure determination of organic molecules. Proton and carbon NMR spectra have many similarities. The scale runs from right to left, and the 0 point is given by the same reference compound. Although it is the proton resonance of tetramethylsilane rather than the carbon resonance that defines here the 0 point. You will notice at once that the scale is much smaller, ranging over only about 12 ppm instead of the 200 ppm needed for carbon. This is because the variation in the chemical shift is a measure of the shielding of the nucleus by the electrons around it. There is inevitably less change possible in the distribution of 2 electrons around a hydrogen nucleus than in that of the 8 valence electrons around a carbon nucleus. Note that this 12 ppm scale is not the same as any part of the carbon NMR spectrum. It is at a different frequency altogether. A reminder, ignore the peak at 7.26 shown in brown. This is from the solvent, as I will explain later. You should know that the position of a signal in an NMR spectrum tells us about its environment. In acetic acid, the methyl group is next to the electron-withdrawing carbonyl group, and so is slightly deshielded at about 2 ppm, and the acidic proton itself, attached to oxygen, is very deshielded at 11.2 ppm. The OH bond is polarized towards oxygen, and the same factor that makes this proton acidic also makes it resonate at low field. So far, things are much the same as in carbon NMR. Now for a difference. In proton NMR, the size of the peaks is also important. The area under the peaks is exactly proportional to the number of protons. Proton spectra are normally integrated. That is, the area under the peaks is computed and recorded as a line with steps corresponding to the area, as it is shown here. Note that it is not enough simply to measure the relative heights of the peaks, because some peaks might be broader than others. Hence, the area under the peak must be measured. After the integration, simply measuring the height of the steps with a ruler gives you the ratio of the numbers of protons represented by each peak. In many spectra, this will be measured for you and reported as a number at the bottom of the spectrum. Following the discovery of the atomic composition from the mass spectrum, we also can elucidate the distribution of protons of various kinds. Here the heights are 6 mm and 18 mm, a ratio of about 1 to 3. The compound is C2H4O2, so, since there are 4 hydrogen atoms altogether, the peaks must represent 1 hydrogen and 3 hydrogens, respectively. In the spectrum of 1,4-dimethoxybenzene, there are just 2 signals in the ratio of 3 to 2. This time, the molecular formula of the compound is C8H10O2, so the true ratio must be 6 to 4, which allows us to have 10 protons in total. The positions of the 2 signals are exactly where you would expect them to be from our discussion of the regions of the NMR spectrum in an earlier module. The aromatic signal for 4 protons is in the left-hand half of the spectrum, between 5 and 10 ppm, where we expect to see protons attached to sp2 carbon atoms, while the signal for 6 protons is in the right-hand half of the spectrum, where we expect to see protons attached to sp3 carbon atoms. In this next example, it is easy to assign the spectrum simply by measuring the steps in the integral. There are 2 identical methyl groups with 6 hydrogens, 1 methyl group by itself with 3 hydrogens, the OH proton, 1 hydrogen, the CH2 group next to the OH 2 hydrogens, and finally, the CH2-CH2 group between the oxygen atoms and the ring for hydrogens. Before we go on, a note about the solvent peaks shown in brown in these spectra. Proton NMR spectra are generally recorded in deuterated chloroform solution, abbreviated as CdCl3. Deuterated chloroform is a chloroform with the only proton replaced by deuterium. The proportionality of the size of the peak to the number of protons tells you why. If you ran a spectrum in normal chloroform, you would see a vast peak for all the solvent hydrogens because there would be much more solvent than the compound you wanted to look at. Using deuterated chloroform cuts out all extraneous protons. Deuterium atoms have different nuclear properties and so do not show up in the proton NMR spectrum. Nonetheless, deuterated chloroform is always unavoidably contaminated with a small amount of chloroform, giving rise to the small peak at 7.26 ppm. Spectra may equally well be recorded in other deuterated solvents such as deuterated water, deuterated dimethyl sulfoxide, or deuterated benzene. All the hydrogen atoms in the last example were attached to sp3 carbons, so you will expect them to fall between 0 and 5 ppm. However, you can clearly see that hydrogen atoms that are nearer to oxygen are shifted downfield within the region to larger delta values, here as far as 3.3 and 3.9 ppm. We can use this fact to build some more detail into our picture of the regions of the proton NMR spectrum. These regions hold for protons attached to carbon. Protons attached to oxygen or nitrogen can come almost anywhere on the spectrum. Even for CH signals, the regions are approximate and overlap quite a lot. Accordingly, you should use this chart as a basic guide, and you should aim to learn these regions. But you will also need to build up a more detailed understanding of the factors affecting proton chemical shift. To help you achieve this understanding, we now need to examine the classes of proton in more detail and examine the reasons for their particular shifts. It is important that you grasp these reasons. In this module, you will see a lot of numbers, chemical shifts, and differences in chemical shifts. I need these to show that the ideas behind proton NMR are securely based in fact. You do not need to learn these numbers. Comprehensive tables will be provided in the lectures of this module, which I hope you will find useful for reference while you are solving problems. We shall start with protons on saturated carbon atoms. The top half of this diagram shows how the protons in a methyl group are shifted more and more as the atom attached to them gets more electronegative. When we are dealing with single atoms as substituents, these effects are straightforward and more or less additive. If we go on adding electronegative chlorine atoms to a carbon atom, electron density is progressively removed from it and the carbon nucleus, and the hydrogen atoms attached to it are progressively deshielded. You can see this in the bottom half of the diagram. Dichloromethane and chloroform are commonly used as solvents, and their shifts will become familiar to you if you look at a lot of spectra. The truth is that chemical shifts and electronegativity are not perfectly correlated. The key property is indeed electron withdrawal, but it is the electron withdrawing power of the whole substituent in comparison with the carbon and hydrogen atoms in the CH skeleton that matters. Methyl groups joined to the same element, say nitrogen, may have very different shifts if the substituent is an amino group or a nitro group. A nitro group is much more electron withdrawing than an amino group. You have seen delta used as a symbol for chemical shift. Now that we have two sorts of chemical shifts, in the carbon NMR spectrum and in the proton NMR spectrum, we need to be able to distinguish them. Accordingly, delta H means chemical shift in the proton NMR spectrum, and delta C is the chemical shift in the carbon NMR spectrum. Concerning the estimation of the chemical shift of a methyl group, what we need is a quick guide rather than some detailed correlations, and the simplest is this. All functional groups except very electron-withdrawing ones shift methyl groups from 1 ppm, where you find them if they are not attached to a functional group, downfield to about 2 ppm. Very electron-withdrawing groups shift methyl groups to about 3 ppm. This is the sort of thing it is worth learning. Rather than trying to fit these data to some atomic property, even such a useful one as electronegativity, we should rather see these shifts as a useful measure of the electron withdrawing power of the group in question. The NMR spectra are telling us about the chemistry. The largest shift you are likely to see for a methyl group is that caused by the nitro group, at least twice the size of the shift for a carbonyl group. This gives us our first hint of some important chemistry. One nitro group is worth 2 carbonyl groups when it comes to electron withdrawing power. You have already seen that electron withdrawal and acidity are related, and in later modules you will see that we can correlate the anion stabilizing power of groups like carbonyl, nitro, and sulfone with proton NMR. It sounds rather unlikely that the humble methyl group could tell us much that is important about molecular structure, but just you wait. We shall look at 4 simple compounds and analyze the chemical shifts of their methyl groups. The first compound, the acid chloride, shows just one methyl signal containing 9 hydrogens at 1.1 ppm. This tells us 2 things. All the protons in each methyl group are identical, and all 3 methyl groups in the tertiary butyl group are identical. This is because rotation about carbon-carbon single bonds is fast. Although at any one instant the hydrogen atoms in one methyl group, or the methyl groups in the tert-butyl group, may differ, on average they are the same. The time averaging process is fast rotation about a sigma bond. The second compound shows 2 signals for the methyl groups, one at 1.99 and one at 2.17 ppm. Unlike a carbon-carbon single bond, the carbon-carbon double bond does not rotate at all, and so the 2 methyl groups are different. One is fixed on the same side of the alkene as the acid chloride group, while the other is fixed on the opposite side. The next pair of compounds contain the formyl group. One is a simple aldehyde, the other an amide of formic acid. It is DMF, dimethylformamide. The first has 2 sorts of methyl groups, a 3-proton signal at 1.81 ppm for the thiomethyl group and a 6-proton signal at 1.35 ppm for the 2 methyl groups. The 2 methyl groups underlined in green are the same, again because of fast rotation about a carbon-carbon sigma bond. The second compound also has 2 methyl signals, at 2.89 and 2.98 ppm, each representing 3 protons, and these are the 2 methyl groups on nitrogen. Restricted rotation about the amide bond must be making the 2 methyl groups different. You should remember from the module on delocalization and conjugation that the amide bond has considerable double bond character because of conjugation, as the lone pair electrons on nitrogen are delocalized into the carbonyl group. Like double bonds, cage structures prevent bond rotation and can make the protons of identical groups appear differently. There are many flavoring compounds, terpenoids, from herbs that have structures like this. In the example here, myrtle, from the myrtle bush, there is a 4-membered ring bridged across a 6-membered ring. The methyl groups on the other bridge are different because one is over the alkene while the other is over the CH2 subunit. No rotation of any bonds within the cage is possible, so these methyl groups are under different environments and resonate at different frequencies. The same is true for the 2 hydrogen atoms of the CH2 group. Electronegative substituents have a similar effect on the protons of CH2 groups and CH groups, but with the added complication that CH2 groups have 2 other substituents in CH groups 3. A simple CH2 group, or methylene, resonates at 1.3 ppm, about 0.4 ppm further downfield than a comparable methyl group, and a simple CH group resonates at 1.7 ppm, another 0.4 ppm downfield. Replacing each hydrogen atom in the methyl group with a carbon atom causes a small downfield shift, as carbon is slightly more electronegative than hydrogen and therefore shields less effectively. The benzyl group is very important in organic chemistry. It occurs naturally in the amino acid phenylalanine you met earlier. Phenylalanine has its CH2 signal at about 3 ppm, which is moved downfield from 1.3 ppm mostly due to deshielding from the benzene ring. Amino acids are often protected as the CBZ or carboxybenzyl derivatives by reaction with an acid chloride. I will discuss this reaction more in the module on protecting groups. Here is a simple example together with the NMR spectrum of the product. Now the CH2 group has gone further downfield to 5.1 ppm as it is next to both oxygen and phenyl, which are electron-withdrawing substituents. A CH group in the middle of a carbon skeleton resonates at about 1.7 ppm. Another 0.4 ppm downfield from a CH2 group in a similar environment. A CH group can have up to 3 substituents, and these will cause further downfield shifts of about the same amount as we have already seen for methyl and CH2 groups. 3 examples from nature possessing a typical CH group are nicotine, the methyl ester of lactic acid, and vitamin C. We shall start with nicotine, which is the compound in tobacco that causes the craving. It has 1 hydrogen atom trapped between a simple tertiary amine and an aromatic ring at 3.24 ppm. The ester of lactic acid has a CH proton at 4.3 ppm. You could estimate this with reasonable accuracy using the guidelines in the 2 summary boxes shown earlier. Take 1.7 for the CH, add 1 for the effect from the carbonyl group, and add 2 for the neighboring OH group. You will get 4.7 ppm. Not far out from the actual chemical shift in the ester of lactic acid. Vitamin C, or ascorbic acid, has 2 CH bonds. One, at 4.05 ppm, is located next to a strong electron-withdrawing OH group. The other one is situated next to a double bond and an oxygen atom, with a chemical shift close to 4.5 ppm. Try to estimate these chemical shifts using the guidelines described earlier. An interesting case is the amino acid phenylalanine, whose CH2 group we looked at a moment ago. It also has a CH group between the amino and the carboxy groups. If we record the proton NMR spectrum in deuterated water, in either basic or acidic solutions, we see 2 different chemical shifts for the CH group. In basic solution, the CH resonates at 3.6 ppm, and in acidic solution, it resonates at 4.35 ppm. There is a double effect here. The carboxyl group and protonated amino group are both more electron-withdrawing than the carboxylate anion and free amino group. Consequently, they both cause the CH group to shift downfield, though to different degrees. For estimating chemical shifts, I suggest you start with a very simple, and therefore necessarily oversimplified, picture, which should be the basis for any further refinements. Start methyl groups at 0.9, methylenes at 1.3, and CH groups at 1.7 ppm. Any functional group is worth a 1 ppm downfield shift except oxygen and halogens, which are worth 2 ppm. This guide is very rough but is easily remembered, and you should aim to learn it. However, if you want to, you can make it slightly more accurate by adding further subdivisions and separating out the very electron-withdrawing groups, such as nitro, ester, and fluoride, which shift by 3 ppm. This gives us the summary chart, which I suggest you use as a reference. The answers deduced from this chart won't be perfect, but will give a good guide. Remember, these shifts are additive. Let's take a simple example, the ketoester on the left. There are just 3 signals, and the integration alone distinguishes the 2 methyl groups from the CH2 group. One methyl has been shifted from 0.9 ppm by about 1 ppm, the other by more than 2 ppm. The first must be next to carbonyl and the second next to oxygen. More precisely, 2.14 ppm is a shift of 1.24 ppm from our standard value for a methyl group, about what we expect for a methyl ketone, while 3.61 ppm is a shift of 2.71 ppm, close to the expected 3 ppm for an ester joined through the oxygen atom. The CH2 group is next to an ester and a ketone carbonyl group, and so we expect it at 3.3 ppm, an accurate estimate as it happens. We shall return to these estimates when we look at the spectra of unknown compounds. In the following lecture, we will focus on the proton signals in the alkene region and the benzene region. Thank you for your attention. Hello everyone and welcome back to the module devoted to proton NMR spectroscopy and its use in determining the structure of organic molecules. In the previous lecture, you saw that proton NMR can be quantified by integrating the area under the signals. We explored the chemical shifts of protons on saturated carbon atoms and the factors influencing the chemical shift. You were also introduced to the main principles used to predict the chemical shift of a proton on a saturated carbon based on the neighboring groups connected to the same carbon. In this lecture, we are going to examine the alkene and benzene regions in proton NMR spectroscopy. In carbon NMR, alkene and benzene carbons came in the same region of the spectrum, but in the proton NMR, the hydrogen atoms attached to arene carbon and alkene carbon atoms sort themselves into 2 groups. To illustrate this point, look at the carbon and proton chemical shifts of cyclohexane and benzene. The 2 carbon signals are almost the same, the difference is less than 1% of the total 200 ppm scale. But the proton signals are very different. 1.6 ppm difference is close to 16% of the 10 ppm scale. There must be a fundamental reason for this. A simple alkene has an area of low electron density in the plane of the molecule because the pi orbital has a node there, and the carbons and hydrogen nuclei lying in the plane gain no shielding from the pi electrons. The benzene ring looks similar at first sight, and the plane of the molecule is indeed a node for all the pi orbitals. However, benzene is aromatic. It has extra stability as the 6 pi electrons fit into 3 very stable orbitals and are delocalized around the whole ring. The applied field sets up a ring current in these delocalized electrons that produces a local field rather like the field produced by the electrons around a nucleus. Inside the benzene ring, the induced field opposes the applied field, but outside the ring it reinforces the applied field. The carbon atoms are in the ring itself and experience neither effect, but the hydrogens are outside the ring. They feel a stronger applied field and appear less shielded. You may think that it is rather pointless imagining what goes on inside an aromatic ring, as we cannot have hydrogen atoms literally inside a benzene ring. However, we can get close. Compounds called cyclophanes have loops of saturated carbon atoms attached at both ends to the same benzene ring. You see here a structure for 7-para-cyclophane, which has a string of 7 CH2 groups attached to the para positions of the same benzene ring. The 4 hydrogen atoms on the benzene ring itself appear as one signal at 7.07 ppm, which is a typical ring current deshielded value for a benzene ring. The 2 CH2 groups joined to the benzene ring are also deshielded by the ring current and appear at 2.84 ppm. The next 2 sets of CH2 groups are neither shielded nor deshielded and show up at 1 ppm. But the middle CH2 group in the chain must be pointing towards the ring in the middle of the pi system and is heavily shielded by the ring current. The chemical shift for the middle CH2 group is in fact minus 0.6 ppm. With a larger aromatic ring, it is possible actually to have hydrogen atoms inside the ring. Compounds are aromatic if they have, for N+2, delocalized electrons, and this ring with 9 double bonds, that is, 18 pi electrons, is aromatic. The hydrogens outside the ring resonate in the aromatic region at rather low field, but the hydrogen atoms inside the ring resonate at an amazing minus 2.9 ppm, showing the strong shielding by the ring current. Such extended aromatic rings are called annulenes. You met them in the module on delocalization and conjugation. The proton NMR spectrum of this simple aromatic amine has 3 peaks in the ratio 1:2:2, which must correspond to the 3 hydrogens of the aromatic ring, 6 hydrogens of the methyl groups connected to the ring, and 6 hydrogens of the methyl groups connected to the nitrogen. The 6.38 ppm signal clearly belongs to the protons around the benzene ring. But why are they so downfield and not at around 7.2 ppm, typical for benzene? We must also distinguish the 2 methyl groups at 2.28 ppm from those at 2.89 ppm. The chart you saw at the end of the previous lecture suggests that these methyl groups should both be at about 2.4 ppm, which is close enough to the number we have for the methyl groups connected to the ring, but not to 2.89 ppm for the methyl groups connected to the nitrogen. The solution to both these puzzles is the distribution of electrons in the aromatic ring. Nitrogen feeds electrons into the pi system by conjugation, making it electron-rich. Accordingly, the ring protons are more shielded, and the nitrogen atom becomes positively charged. As a result, its methyl groups are more deshielded. Therefore, the peak at 2.89 ppm must belong to the dimethylamino group. Other groups, such as simple alkyl groups, hardly perturb the aromatic system at all, and it is quite common for all 5 protons in an alkyl benzene to appear as one signal instead of the 3 we might expect. Here is an example with some non-aromatic protons too. You saw another in the previous lecture for the benzyloxycarbonyl protected amino acid. The 5 protons on the aromatic ring all have the same chemical shift. Check that you can assign the rest. The methoxy group is typical of a methyl ester and appears at 3.73 ppm. One of the CH2 groups is between 2 carbonyl groups and shows up at 3.37 ppm. The other CH2 group is next to an ester and a benzene ring. If we try estimate its chemical shift, then we will get 5.8 ppm, which is reasonably close to the observed 5.19 ppm. Notice how the phenyl and the oxygen together act to shift the hydrogens attached to this sp3 carbon downfield into what we usually expect to be the alkene region. You should not interpret the regions I introduced earlier too rigidly. We can get an idea of the effect of electron distribution by looking at a series of benzene rings with the same substituent in the 1 and 4 positions. This pattern makes all 4 hydrogens on the ring identical. Here are a few compounds listed in order of chemical shift, largest shift, or most deshielded, first. Conjugation is shown by the usual curly arrows, and inductive effects via a straight arrow by the side of the group. For simplicity, only 1 hydrogen atom and 1 set of arrows are shown. The largest shifts come from groups that withdraw electrons by conjugation. Nitro is the most powerful electron-withdrawing group by conjugation. This should not surprise you, as we saw the same in non-aromatic compounds in both carbon and proton NMR spectra. Then comes the carbonyl and nitro group, followed by groups showing simple inductive withdrawal. An important example is the trifluoromethyl group, which demonstrates inductive withdrawal as the 3 fluorine atoms combine to exert a powerful inductive effect. I hope you remember that conjugation is felt through pi bonds, while inductive effects are the result of electron withdrawal or donation felt simply by polarization of the sigma bonds of the molecule. In the middle of our sequence, around the position of benzene itself at 7.27 ppm, come the halogens, whose inductive electron withdrawal and lone pair donation are nearly balanced. Alkyl groups are weak inductive donators, but the groups which give the most shielding are those containing the electronegative atoms oxygen and nitrogen. The carbon-oxygen and carbon-nitrogen sigma bonds are polarized with a partial positive charge on the carbon. Nevertheless, despite being inductively electron-withdrawing, on-balance conjugation of lone pairs of nitrogen and oxygen with the ring makes them net electron donors. They increase the shielding at the ring hydrogens, and amino groups are the best in this. Note that one nitrogen-based functional group, nitro group, is the best electron withdrawal, while another, amino group, is the best electron donor. As far as the donors with lone pairs are concerned, 2 factors are important: the size of the orbitals with the lone pairs and the electronegativity of the element. If we look at the 4 halides, the lone pairs are in 2p orbitals for fluorine, 3p orbitals for chlorine, 4p orbitals for bromine, and 5p orbitals for iodine. In all cases, the orbitals on the benzene ring are 2p, so the fluorine orbital is of the right size to interact well. Even though fluorine is the most electronegative, it is still the best donor by conjugation. The others do not pull so much electron density away, but they cannot give so much back either, as the orbitals of the lone pairs are too big and do not interact well with the 2p orbitals of the benzene ring. If we compare the first row of the p-block elements, fluorine, oxygen, and nitrogen, all have lone pairs and two p orbitals, so now electronegativity is the only variable. As you would expect, the most electronegative element, fluorine, is now the weakest donor. All of these factors have very important consequences for the reactivity of differently substituted benzene rings, which will be discussed in a later module. The same sort of thing happens with alkenes. I will concentrate on cyclohexane so as to make a good comparison with benzene. The 6 identical protons of benzene resonate at 7.27 ppm. The 2 identical alkene protons of cyclohexane resonate at 5.68 ppm. A conjugating and electron-withdrawing group, such as a ketone, removes electrons from the double bond as expected, but unequally. The proton nearer the carbonyl group is only slightly downfield from cyclohexane, but the more distant one is over 1 ppm downfield. The curly arrows show the electron distribution, which we can deduce from the NMR spectrum. The effect of oxygen as a conjugating electron donor is even more dramatic. It shifts the proton next to it downfield by the inductive effect, but pushes the more distant proton upfield a whole 1 ppm by donating electrons. Here, the separation between the two protons is nearly 2 ppm. For both types of substituents, the effects are more marked on the more distant beta proton. If these shifts reflect the true electron distribution, we should be able to deduce something about the chemistry of the following 3 compounds. You might expect that nucleophiles will attack the electron-deficient site in the nitroalkene, while electrophiles will be attacked by the electron-rich sites in silyl-enol ethers and enamines. These are all important reagents and do indeed react as we predict, as you will see in later modules. Just look at the chemical shifts. There is nearly a 3 ppm difference between the shifts of the same proton on the nitro compound and the enamine. Alkene protons on different carbon atoms can obviously be different if the carbon atoms themselves are different, and you have just seen examples of that. Alkene protons can also be different if they are on the same carbon atom. All that is necessary is that the substituents at the other end of the double bond should themselves be different. The silyl-enol ether and the unsaturated ester shown here both fit into this category. The protons on the double bond must be different because each assists to a different group. We may not be able to assign which is which, but the difference alone tells us something. The third compound is an interesting case. The different shifts of the two protons on the ring prove that the nitrogen-chlorine bond is at an angle to the carbon-nitrogen double bond. If it were in line, the two hydrogens would be identical. The other side of the carbon-nitrogen double bond is occupied by a lone pair, and the nitrogen atom is trigonal, sp2 hybridized. In other words, we have a type of cis-trans isomerism in this system. To sum it up, in this lecture, you learned about the alkene and benzene regions of proton NMR spectroscopy. I discussed the reasons behind the deshielding effect of arones and alkenes on the protons connected to a benzene ring and a double bond. You saw how conjugation and inductive effects affect the chemical shift of protons in substituted arones and alkenes. NMR can be used to predict the reactivity of organic molecules and the selectivity of reactions involving certain molecules. The following lecture will concentrate on the proton NMR of the aldehyde region and the description of the chemical shifts of protons connected to a heteroatom. Thank you for your attention. Greetings to all, and welcome back to the lecture series focused on determining the structure of organic molecules through proton NMR spectroscopy. In the previous lectures, you were introduced to the main principles of NMR spectroscopy, learning about the regions where protons bound to saturated carbons, alkenes, and arones appear. You were also introduced to the factors influencing chemical shifts in proton NMR spectroscopy. In this lecture, we will specifically focus on the proton NMR of hydrogens bound to unsaturated carbons next to oxygen. Additionally, you will become familiar with the typical signals for protons connected to a heteroatom. The aldehyde proton is unique. It is directly attached to a carbonyl group, one of the most electron-withdrawing groups that exists. It is therefore very deshielded and resonates with the largest shifts of any CH protons, typically in the 9 to 10 ppm region. The examples shown here are all compounds that we have met before. 2 are just simple aldehydes, aromatic and aliphatic. The third is the solvent dimethylformamide, abbreviated as DMF. The formal proton of DMF is less deshielded than most, as the amide delocalization that feeds electrons into the carbonyl group provides some extra shielding. Conjugation with an oxygen lone pair has much the same effect, Formate esters resonate at about 8 ppm. However, conjugation with pi bonds does not have the same shielding effect. The aromatic aldehyde above, simple conjugated aldehyde below, and the natural product mertanol all have formal protons in the normal region, between 9 and 10 ppm. Two other types of protons resonate in the region around 9 ppm, some aromatic protons and some protons attached to heteroatoms like OH and NH. We will deal with NH and OH protons in the next section, but first we must look at some electron-deficient aromatic rings with distinctively large shifts. Protons on double bonds, even very electron-deficient double bonds like those of nitroalkenes, hardly get into the aldehyde region. However, some benzene rings with very electron-withdrawing groups do manage it because of the extra downfield shift of the ring current, so look out for nitrobenzenes as they may have signals in the 8 to 9 ppm region. More important molecules with signals in this region are the aromatic heterocycles such as pyridine, which you saw functioning as a base. The NMR shifts clearly show that pyridine is aromatic. One proton is at 7.1 ppm, essentially the same as benzene, but the others are more downfield and one, at C2, indicated in black, is in the aldehyde region. This is not because pyridine is more aromatic than benzene, but because nitrogen is more electronegative than carbon. Position 2 is like an aldehyde, a proton attached to sp2 carbon bearing a heteroatom, while position 4 is electron-deficient due to conjugation as the electronegative nitrogen is electron-withdrawing. Note that the alternative conjugation shown in the structure below is wrong. The generated structure with two adjacent double bonds in a six-membered ring is impossible. In any case, the lone pair electrons on nitrogen are in an sp2 orbital orthogonal to the p orbitals in the ring, and there is no interaction between orthogonal orbitals. Isoquinoline is a pyridine and a benzene ring fused together and has a proton even further downfield at 9.1 ppm. The proton indicated in black is more like an imine proton that experiences the ring current of the benzene ring. Protons directly attached to oxygen, nitrogen, sulfur, or any other heteroatom also have signals in the NMR spectrum. I have avoided them so far because the positions of these signals are less reliable and because they are affected by proton exchange. The proton NMR of the antioxidant BHT is very simple, consisting of just 4 signals with integrals 2, 1, 3, and 18. The chemical shifts of the tert-butyl group indicated in brown, the methyl group on the benzene ring shown in orange, and the 2 identical aromatic protons highlighted in green should cause you no surprise. What is left? The 1H signal at 5.4 ppm must be the OH. Earlier in this module, you saw the spectrum of acetic acid, which showed an OH resonance at 11.2 ppm. Simple alcohols such as tert-butanol have OH signals in deuterated chloroform at around 2 ppm. You may ask, why do we have such a big difference? This is just a matter of acidity. The more acidic a hydrogen is, that is, the more easily it can escape as a proton, the more the OH bond is polarized towards oxygen. The more the OH bond is polarized, the closer we are to free proton, which would have no shielding electrons at all, and so the further the proton goes downfield. The OH chemical shifts and the acidity of the OH group are, to a rough extent at least, related. Thiols behave in a similar way to alcohols but are not so deshielded, as you would expect from the smaller electronegativity of sulfur. Alkane thiols appear at about 2 ppm and aryl thiols, or thiophenols, at about 4 ppm. Amines and amides show a big variation as you would expect for the variety of functional groups involved and are summarized here. Amides are slightly acidic and amide protons resonate at quite low fields. Pyrroles are special as the aromaticity of the ring makes the NH proton unusually acidic, and they appear at about 10 ppm. Compounds with very polar groups often dissolve best in water. NMR spectra are usually run in deuterated chloroform, but heavy water, or deuterated water, can also be an excellent NMR solvent. Here are some proton NMR spectra measured in deuterated water. Glycine is expected to exist as its zwitterion. It has a signal for 2 hydrogens, shown in green, for the CH2 between the 2 functional groups, which would do for either form. The signal for 3 hydrogens highlighted in orange might suggest the protonated amino group, but wait a moment before making up your mind. The aminothiol salt has the methyl and CH2 groups about where we would expect them, but the protons of SH and protonated amino groups appear as one signal close to the region of the protonated amine in glycine. The double salt of ethylene-diamine tetraacetic acid, or EDTA, has several curious features. The two CH2 groups shown in green are fine, but the other four CH2 groups all appear identical, as do all the protons on both the carboxyl and amino groups. The best clue to why this is so comes from the strange coincidence of the chemical shifts of the OH, NH, and SH protons in these molecules. They are all the same with an experimental error. For 0.9 ppm for glycine, for 0.8 ppm for the aminothiol, and 4.8 ppm for EDTA. In fact, all correspond to the same species, semi-heavy water or monodeutyrated water. The exchange between acidic protons is extremely fast, and the solvent, deuterated water in this case, supplies a vast excess of exchangeable deuteriums. These immediately replace all the OH, NH, and SH protons in the molecules with deuteriums, forming monodeutyrated water in the process. Recall that we do not see signals for deuterium atoms, that is why deuterated solvents are used. The same sort of exchange between OH or NH protons with each other or with traces of water in the sample means that the OH and NH peaks in most spectra are broader than the peaks for CH protons. Two questions remain. First, can we tell whether glycine is its zwitterine in water or not? Second, why are all four CH2 groups in EDTA the same? Glycine is not fully transferred into its zwitterine in water as there is an equilibrium between the two forms of glycine. This we can answer. Regarding the second question, as there is an equilibrium exchanging protons between the carboxyl group and the solvent, there will be an equally fast equilibrium exchanging protons between the deuterated carboxyl groups and carboxylates. This makes all four arms of EDTA the same. You should leave this lecture with an important chemical principle firmly established in your mind. Proton exchange between heteroatoms, particularly oxygen, nitrogen, and sulfur, is a very fast process in comparison with other chemical reactions and often leads to averaged peaks in the proton NMR spectrum. I mentioned this fact before in the context of the mechanism of acid-catalyzed addition to a carbonyl group, and we will continue to explore the mechanistic consequences of fast proton transfers throughout this course. To summarize, in this lecture, we observed that in proton NMR, the most deshielded protons are those connected to the carbon of a carbonyl group. However, it is important to keep in mind that protons in arones possessing strong electron-withdrawing groups and six-membered aromatic heterocycles can appear in the same region as the protons from aldehydes. The protons connected to a heteroatom can appear anywhere in the NMR spectra, though there is some correlation between acidity and the chemical shift of hydrogens connected to oxygen atoms. Depending on the solvent, in molecules possessing acidic protons, there can be fast exchange of the acidic protons between functional groups, typically resulting in equilibration and broad signals for the acidic protons. In the following lectures, our main focus will be on the examination of the coupling between neighboring protons and its use in the determination of the structure of organic molecules. Thank you for your attention. Greetings to all, and welcome back to the module devoted to proton NMR spectroscopy. In the previous lectures, we learned the main principles of NMR spectroscopy. You were introduced to proton NMR and the regions where protons bound to different functional groups appear. We also discussed how electron-withdrawing and electron-donating substituents affect the chemical shifts of nearby protons. So far, proton NMR has been not unlike carbon NMR on a smaller scale. However, we have yet to discuss the real strength of proton NMR, something more important than chemical shifts and something that allows us to look not just at individual atoms but also at the way the CH skeleton is joined together. Here's the result of the interaction between nearby protons, known as coupling. An example I could have chosen in the last lecture is the nucleic acid component cytosine, which is one of the four bases that, in combination with deoxyribose and phosphate, make up DNA. It is a member of the class of heterocycles called pyrimidines. Cytosine has exchanging NH2 and NH protons, giving a peak for semi-heavy water at 4.5 ppm. I did not discuss this example up to this point because the other two peaks for the aromatic hydrogens would have puzzled you. Instead of giving just one line for each proton, the aromatic hydrogens give two lines each, doublets, as you will learn to call them, and now is the time to discuss the origin of this coupling. You might have expected a spectrum like that of the heterocycle shown here, which like cytosine is also a pyrimidine. This one also has exchanging NH2 protons and 2 protons on the heterocyclic ring. But unlike cytosine, these two protons give the expected 2 lines, or singlets, for the aromatic protons instead of the 4 lines in the cytosine spectrum. It is easy to assign this spectrum. The green proton labeled HA is attached to an aldehyde-like carbon-nitrogen double bond and so comes at lowest field. The red proton labeled HX is ortho to 2 electron-donating amino groups and so comes at high field for an aromatic proton. These protons do not couple with each other because they are too far apart. They are separated by 5 bonds, whereas the ring protons in cytosine are separated by just 3 bonds. Understanding this phenomenon is so important that I am going to explain it in 3 different ways. You choose which appeals to you most as each method offers a different insight. The diaminopyrimidine spectrum you have just seen has 2 single lines because each proton in the ring can be aligned either with or against the applied magnetic field. From now on we shall call such signals singlets. The cytosine spectrum is different because each proton is near enough to experience the small magnetic field of the other proton as well as the field of the magnet itself. This diagram shows the result of such interaction. If each proton interacted only with the applied field, we would get 2 singlets. But proton HA actually experiences 2 slightly different fields, the applied field plus the field of nearby HX proton, or the applied field minus the field of nearby HX proton. In other words, HX proton acts either to increase or decrease the field experienced by HA proton. The position of a resonance depends on the field experienced by the proton, so these 2 situations give rise to 2 slightly different peaks, a doublet, as we shall call it. Whatever happens to the HA proton is also experienced by the HX proton, so the spectrum has 2 doublets, one for each proton. We can say that each proton couples with the other. The field of a proton is very small indeed in comparison with the field of the magnet, and the separation between the lines of a doublet is very small. We shall discuss the size of the coupling later. The second explanation takes into account the energy levels of the nucleus. When we discussed chemical bonds, we imagined electronic energy levels on neighboring atoms interacting with each other and splitting to produce new molecular energy levels, some higher in energy and some lower in energy than the original atomic energy levels. When hydrogen nuclei are near each other in a molecule, the nuclear energy levels also interact and split to produce new energy levels. If a single hydrogen nucleus interacts with a magnetic field, we have the following picture. There are 2 energy levels as the nucleus can be aligned with or against the applied magnetic field. There is 1 energy jump possible, and there is a resonance at 1 frequency. The spectrum of the diaminopyrimidine shows exactly this situation. The 2 protons are well separated in the molecule, and each behaves independently. Each has 2 energy levels, each gives a singlet, and there are 2 lines in the spectrum. But in cytosine the situation is different. Each hydrogen atom has another hydrogen nucleus nearby, and there are now 4 energy levels. Each nucleus of HA proton and HX proton can be aligned with or against the applied field. There is 1 lower energy level where they are both aligned with the field and 1 higher level where they are both aligned against the applied field. In between, there are 2 different energy levels in which 1 nucleus is aligned with the field and 1 against. Exciting proton from alignment with to alignment against the applied field can be done in 2 slightly different ways, shown as A1 and A2 on the diagram. The result is 2 resonances very close together in the spectrum. Please note that we cannot have this discussion about HA proton without discussing HX proton in the same way. If there are 2 slightly different energy jumps to excite HA proton, there must also be 2 slightly different energy jumps to excite HX proton. The energy jumps indicated as A1, A2, X1, and X2 are all different, but the difference between A1 and A2 is exactly the same as the difference between X1 and X2. Each proton now gives 2 lines, a doublet, in the NMR spectrum, and the splitting of the 2 doublets is exactly the same. We describe this situation as coupling. We say HA and HX protons are coupled. I will be using this language from now on, and so must you. Now let's look back at the spectrum of cytosine you saw earlier. You can see the 2 doublets, 1 for each of the protons on the aromatic ring. Each is split by the same amount, and this is easy to check with a ruler. The separation of the lines is the coupling constant and is indicated as J. In this case, the coupling constant J equals 4 Hz. You may ask, why do we measure the coupling constant in Hertz and not in ppm? I mentioned earlier that we measure chemical shifts in ppm, so we can get the same number regardless of the power of the NMR machine. We measure the coupling constant in Hertz as this allows us to get the same number regardless of the operating power of the machine. These are proton NMR spectra of the same compound run on two different NMR machines, one on a 90 MHz spectrometer and one on a 300 MHz spectrometer. These are at the lower and upper ends of the range of field strengths in common use. Notice that the peaks stay in the same place on the chemical shift scale, ppm, but the size of the coupling appears to change because 1 ppm is worth 90 Hz in the top spectrum but 300 Hz in the bottom. To measure a coupling constant, it is essential to know the power of the NMR machine in megahertz. This is why you were told that each illustrated spectrum is, say, a 400 MHz proton NMR spectrum. Couplings may be marked on the spectrum, electronically, but if not, then to measure the coupling, measure the distance between the lines by ruler or dividers and use the horizontal scale to find out the separation in ppm. The conversion is then easy. To turn parts per million into Hertz, you just leave out the million. So 1 ppm on a 300 MHz machine is 300 Hz. When you change from one machine to another, say, from a 200 MHz to a 500 MHz NMR machine, chemical shifts stay the same in ppm and coupling constants stay the same in Hertz. Now for the third way to describe coupling. If you look again at what the spectrum would be like without interaction between HA and HX protons, you will see the pattern shown here, with the chemical shift of each proton clearly obvious. But for cytosine, you do not see this because each proton couples with the other and splits its signal by an equal amount on either side of the true chemical shift. In other words, the true spectrum of cytosine has a pair of doublets each split by an identical amount. Note that no line appears at the true chemical shift, but it is easy to measure the chemical shift by taking the midpoint of the doublet. So, the spectrum of cytosine would be described as it is shown here. The main number gives the chemical shift in ppm and then, in brackets, comes the integration as the number of hydrogens, the shape of the signal, here D for doublet, the size of coupling constants in Hertz, and the assignment of protons, usually related to the figure of the structure. The integration refers to the combined area under both peaks in the doublet. If the doublet is exactly symmetrical, each peak integrates into half a proton. The combined signal, although complicated, integrates to the right number of protons. If there are more protons involved, the splitting process continues. Here is the NMR spectrum of a famous perfumery compound supposed to have the smell of green leaf lilac. The compound is an acetal with 5 nearly identical aromatic protons at the normal benzene position and 6 protons on 2 identical methoxy groups. It is the remaining 3 protons that interest us. They appear as a doublet for 2 hydrogens at 2.9 ppm and a triplet for 1 hydrogen at 4.6 ppm. In NMR terminology, triplet means 3 equally spaced lines in the ratio 1 to 2 to 1. The triplet arises from the 3 possible states of the 2 identical protons in the CH2 group. If one HA proton interacts with 2 HX protons, it can experience the HX protons in 3 different possible states. First, both HX protons can be aligned with the applied field, or both can be aligned against the applied field. These states will increase or decrease the applied field just as before. But if one of HX protons is aligned with the applied field while the other is aligned against the applied field, there is no net change to the field experienced by the HA proton. Accordingly, there are 2 arrangements for these interactions. We will therefore see a signal of double intensity for the HA proton at the correct chemical shift, along with 1 signal at higher field and 1 at lower field. In other words, a triplet with an intensity of 1 to 2 to 1. We can examine this result using our second method. There is one way in which both nuclei can be aligned with the applied field and another way in which both can be aligned against it. In contrast, there are 2 ways in which only one of the nuclei is aligned with the applied field. The HA proton interacts with each of these states, resulting in a triplet with signal intensities of 1 to 2 to 1. Using our third method to understand coupling and observe how the triplet arises, we can see the peaks split in successive stages, as described here. If there are more protons involved, we continue to get more complex systems, but the intensities can all be deduced simply from Pascal's triangle, which gives the coefficients in a binomial expansion. If you are unfamiliar with this simple device, here it is. To construct Pascal's triangle, start by placing 1 at the top of the triangle. Then, in each subsequent line, add an extra number by summing the 2 numbers on either side of the new number in the line above. If there is no number on one side, treat it as 0. Consequently, the lines always begin and end with 1. You can read off from the triangle what pattern you may expect when a proton is coupled to N equivalent neighbors. There are always N+1 peaks with the intensity shown by the triangle. So far, you have seen 1-to-1 doublet from coupling to one proton, which corresponds to the line 2 of the triangle, and 1-to-2-to-1 triplet from coupling to two neighboring protons. You will often meet ethyl groups, where the CH2 group couples to three identical protons and appears as a 1-3-3-1 quartet, and the methyl group as a 1-2-1 triplet. In the isopropyl group, the methyl groups appear as a doublet, and the CH group as septuplet. Here's a simple example: the four-membered cyclic ether oxetane. Its NMR spectrum has a triplet for the two identical CH2 groups next to oxygen and a quintet for the CH2 group in the middle. Each HX proton, underlined in red, sees four identical neighbors and is split equally by them all to give a quintet with the ratio 1, 4, 6, 4, 1. Each HA proton, underlined in green, sees two identical neighbors and is split into a triplet with a ratio of 1-to-2-to-1. The combined integral of all the lines in the quintet together is 2, and of all the lines in the triplet is 4. Remember, the coupling comes only from the neighboring protons. It does not matter how many protons form the signal. What matters is the number of protons next door. The protons in each CH2 group are identical and cannot couple with themselves. A slightly more complicated example is the diethyl acetal shown here. It has a simple pair of doublets for the two protons on the backbone indicated in red and green, and a typical ethyl group containing a quartet for the CH2 groups and a triplet for the methyl groups. An ethyl group is attached to only one substituent through its CH2 group, so the chemical shift of that CH2 group tells us what it is bound to. Here, the peak at 3.76 ppm can only come from an ethoxy group, and there are, of course, two identical CH2 groups in this molecule. In the molecules described so far, a proton may have had several neighbors, but all those neighbors have been the same. Therefore, all the coupling constants have been the same. But what happens when coupling constants differ? For xanthemic acid, the structural core of the insecticides produced by pyrethrum flowers gives an example of the simplest situation where a proton has two different neighbors. Xanthemic acid has a carboxylic acid, an alkene, and two methyl groups on the three-membered ring. The HA proton has two neighbors, indicated as HX and HM. The coupling constant to the HX proton is 8 Hz, and that to the HM proton is 5.5 Hz. We can construct the splitting pattern for the HA proton as shown on the right. The result is 4 lines of equal intensity called a double doublet, or sometimes a doublet of doublets, abbreviated as DD. The smaller coupling constant can be read off from the separation between lines 1 and 2, while the larger coupling constant is between lines 1 and 3. The separation between the middle two lines is not a coupling constant. You could view a double doublet as an imperfect triplet where the second coupling is too small to bring the central lines together. Alternatively, look at a triplet as a special case of a double doublet where the two couplings are identical and the two middle lines coincide. To sum it up, in this lecture, we have learned that protons on adjacent carbon atoms couple together, resulting in a splitting of corresponding signals. The coupling constants are measured in Hertz to ensure that the absolute values are not changed when changing the power of the NMR machine. We went through 3 relevant methods that can be used to predict the splitting patterns in proton NMR spectroscopy. A very useful tool is Pascal's triangle, which can be applied as a guide to predict the coupling between protons on neighboring carbon atoms. We saw that hydrogen atoms surrounded by 2 different neighboring hydrogens split with 2 different coupling constants. In the following lecture, we will examine the factors controlling the coupling constants in proton NMR spectroscopy, long-range couplings, and other relevant topics. Thank you for your attention. Hello everyone, and welcome to the concluding session of the series of lectures describing proton NMR spectroscopy and its implications in determining the structure of organic molecules. In the previous lecture, we started examining the phenomenon of coupling between protons connected to adjacent carbon atoms. You saw that the splitting of the signals of a given proton depends on the number of neighboring hydrogen atoms and the nature of the neighboring protons. You learned that the splitting of the signal and the relevant intensities in the splitting can be effectively predicted by Pascal's triangle. If a proton has more than one neighboring hydrogen atom, and these hydrogens are not similar, then we get a splitting for the signal with different coupling constants. In this lecture, we will continue examining relevant effects conditioning the coupling between neighboring protons and explore how the obtained information can be used to elucidate the connectivity of functional groups by proton NMR spectroscopy. First, we should answer the following question. Do neighboring nuclei interact through space or through the electrons in the bonds? We know that coupling is in fact a through-bond effect because of the way coupling constants vary with the shape of the molecule. The most important case occurs when the protons are at either end of a double bond. If the two hydrogens are cis, the coupling constant, indicated as J, is typically about 10 Hz. But if they are trans, the coupling constant is much larger, usually between 15 and 18 Hz. These two chloroacids are good examples. If coupling were through space, the nearer cis hydrogens would have the larger coupling constant. In fact, coupling occurs through the bonds, and the more perfect parallel alignment of the bonds in the trans compound provides better communication and a larger coupling constant. Coupling is at least as helpful as chemical shift in assigning spectra. When I was describing the olefin region in proton NMR spectroscopy, I assigned specific chemical shifts for the protons indicated as H3 and H2, and you might be wondering, how did I know that? It was the coupling that told me the answer. The proton next to the carbonyl group, indicated as H2, has one neighbor, indicated as H3, and appears similar to a doublet with coupling constant 11 Hz, just right for a proton on a double bond with a cis neighbor. The proton H3 itself appears as a double triplet. Inside each triplet, the separation of the lines is 4 Hz, and the two triplets are 11 Hz apart. The coupling of H3 is as complex as you have seen yet, but it can be represented diagrammatically by the same approach we have taken before. Accordingly, in the signal of H3 proton, the 4 Hz separation of the lines is caused by the coupling with the protons indicated as H4. And the 11 Hz separation in the two triplets is caused by the coupling with the proton indicated as H2. As coupling becomes more complicated, interpreting the results can be challenging, but with a clear understanding of what to look for, things become easier. Here is an example of heptantuone, which is bezoalarm pheromone. The green protons next to the carbonyl group form a triplet for the two hydrogens coupled to the two red neighboring protons, with a coupling constant of 7 Hz. The red protons themselves are adjacent to 4 protons, and although these 4 protons are not identical, the coupling constants are about the same because the neighboring protons are similar. Therefore, the protons underlined in red appear as a quintet for 2 hydrogens with a coupling constant of about 7 Hz. The brown signal is more complicated. We might call it a multiplet for 4 hydrogens, but in fact, we know what it must be, as the signals for the 4 brown protons on carbons 5 and 6 overlap. It must be made up of a quintet for the protons on C5 and a sextet for the protons on C6. We can observe the coupling of the protons on C6 with the terminal methyl group, as the methyl group, underlined in orange, is a triplet for 3 hydrogens with a 7 Hz coupling constant. The coupling constants in cyclohexane were different, but in heptanone, all the coupling constants are approximately the same, around 7 Hz. In general, the most important factors affecting coupling constants are the distance between the protons, the angle between the two CH bonds, and the presence of electronegative substituents. The coupling constants we have seen so far have all been between hydrogen atoms on neighboring carbon atoms. In other words, the coupling is through 3 bonds, hydrogen-carbon-carbon-hydrogen, and is designated as shown here. These coupling constants are usually about 7 Hz in an open-chain, freely rotating system, such as we have in the bezoalarm pheromone. In such systems, the difference in the length of CH bonds is very little, but in cyclohexane, there is a carbon-carbon double bond, which is significantly shorter than a single bond. Therefore, couplings across double bonds are usually larger than 7 Hz and vary between 9 and 18 Hz. The coupling constants shown here are called vicinal couplings because the protons concerned are on neighboring carbon atoms. Something else is different too. In an open-chain system, we have a time average of all rotational conformations. But across a double bond, there is no rotation and the angle between the two CH bonds is fixed. They're always in the same plane. In the plane of the alkene, the CH bonds are either at 60 degrees when they are cis or 180 degrees when they are trans to each other. Coupling constants in benzene rings are slightly less than those across cis alkenes because the bond is slightly longer. The bond order in benzene is 1.5 rather than 2. In naphthalenes, there are unequal bond lengths around the 2 rings. The bond between the 2 rings is the shortest, and the lengths of the others are shown on the left. Accordingly, the coupling across the shorter bond is significantly stronger than the coupling across the longer bond. The effect of the third factor, electronegativity, is easily seen in the comparison between ordinary alkenes and alkenes with alkoxy substituents, known as enol ethers. We are going to compare two pairs of compounds with a cis or a trans double bond. One pair has a phenyl group at one end of the alkene and the other has a phenoxy group. For both pairs, the trans coupling is larger than the cis, as you would expect from the more perfect parallel alignment of the bonds in the trans compounds. But if you compare the two pairs, the enol ethers have much smaller coupling constants. The trans coupling for the enol ethers is only slightly larger than the cis coupling in common alkenes. The electronegative oxygen atom is withdrawing electrons from the CH bonds in the enol ethers, which is weakening the communication for the nuclei through the bonds. When the through-bond distance gets longer than 3 bonds, coupling is not usually seen. To put it another way, the coupling through 4 bonds is usually 0. However, it is seen in some special cases, the most important being meta-coupling in aromatic rings and allylic coupling in alkenes. In both, the orbitals between the two hydrogen atoms can line up in a zigzag fashion to maximize interaction. This arrangement looks rather like the letter W, and this sort of coupling is called W coupling. Even with this advantage, values of the coupling through 4 bonds are usually small and vary between 1 and 3 Hz. Meta-coupling is very common when there is orthocoupling as well, but here is an example where there is no orthocoupling because none of the aromatic protons have immediate neighbors. The only coupling seen is the meta-coupling. There are 2 identical protons indicated as HA, which have one meta-neighbor and appear as a doublet for 2 hydrogens. The proton between the 2 methoxy groups has 2 identical meta-neighbors and so appears as a triplet for 1 hydrogen. The coupling is small and does not exceed 2.5 Hz. You have already seen a molecule with allylic coupling, although I did not put too much stress on that. I discussed in some detail why cyclohexanone has a double triplet for the proton indicated as H3, but it also has a less obvious double triplet for the proton described as H2. The triplet coupling is less obvious since the coupling through 4 bonds is small and does not exceed 2 Hz. Below, you can see the diagram of the coupling, which you could spot in an expansion of the signal underlined in green in the cyclohexanone spectrum. Identical protons normally do not couple with each other. The 3 protons in a methyl group may couple to some other protons, but never couple with each other. Normally, identical neighbors do not couple either. Even though each of the 4 protons on the paradise-substituted benzenes has one neighbor, they appear as one singlet because every proton is identical to its neighbor. We have also seen how 2 different protons give 2 separate doublets. Now we need to see what happens to protons in between these 2 extremes. What happens to 2 similar neighbors? As 2 protons get closer and closer together, do the 2 doublets you see in these systems collapse into a singlet? Suppose we have 2 different neighbors on an aromatic ring as it is demonstrated in some of these spectra. 3 of the examples shown here are 1, 4 di-substituted benzene rings with different groups at the 1 and 4 positions. You will notice that when the 2 doublets are far apart, as in the first spectrum, they look like normal doublets. But as they get closer together, the doublets get more and more distorted, until finally they are identical and collapse to a singlet for 4 hydrogens. The critical factor in the shape of the peak is how the difference between the chemical shifts of the 2 protons compares with the size of the coupling constant for the NMR machine in question. If the difference between the chemical shifts is much larger than the coupling constant for the NMR machine, then there is no distortion, and we have a spectrum of 2 doublets. As the difference between the chemical shifts approaches the coupling constant for the NMR machine, the inner lines of the 2 doublets increase, and the outer lines decrease until the outer lines vanish altogether, leaving us with the 2 superimposed inner lines for a singlet. You can see this progression in the diagram on the right. Depending on the substituents in the benzene ring, the 2 inner lines in the signals may be closer than the gap between the doublets, or even the 4 lines may all be equally spaced. You may see this situation described as a quartet. In reality, it is not a quartet. A quartet has exactly equally spaced signals with intensities 1, 3, 3, 1, arising from coupling to 3 identical protons, and you should avoid this misleading usage for such systems. Several versions of distorted doublets were shown in the previous diagrams, and there are many more variations available. It is a generally useful tip that a distorted doublet points towards the protons with which it is coupled. In other words, the signal of distorted doublets is roofed, with the usual arrangement of low walls and a high middle. So look out for doublets or any other coupled signals of this kind. We shall end this section with a final example illustrating roofing, the combination of doublets with roofing and allylic coupling in paradise-substituted benzenes. The aromatic ring protons form a pair of distorted doublets, indicating that the compound is a paradise-substituted benzene. Then, the alkene protons form the distorted doublet combined with a pair of doublets. They are coupled to each other, with a large coupling constant indicating on a trans arrangement, and one of the protons in the alkene region is also coupled to another distant allylic proton. The large doublets in the alkene region are distorted, but the small doublets within the right-hand half of the system are equal in height. The distant allylic proton is part of an isopropyl group and is coupled to the alkene proton underlined in orange and the 6 identical methyl protons. Both coupling constants are nearly the same, so it is split by 7 protons and is an octuplet. It looks like a sextuplet because the difference between the intensity ratios of the lines in an octuplet is exceedingly large, so it is not surprising that the outside lines of the octuplet are hardly visible. In the lecture covering the alkene region in proton NMR spectroscopy, we have seen cases where protons on the same carbon atom are different, such as in compounds with an alkene unsubstituted at one end. If neighboring protons are different, then they should couple. Indeed, they do couple, but in this case, the coupling constant is usually very small. Here's the spectrum of a silylenol ether you met earlier. The small 1.4 Hz coupling is a coupling through 2 bonds between 2 protons on the same carbon that are different because there is no rotation about the double bond. The coupling through 2 bonds is alternatively called geminal coupling. This means that a monosubstituted alkene, a vinyl group, will have characteristic signals for each of the 3 protons on the double bond. Here is an example with ethyl acrylate, a monomer for the formation of acrylic polymers. The spectrum may seem complex at first, but it is easy to sort out using the characteristic coupling constants for geminal couplings. The largest coupling constant is 16 Hz and is obviously between the orange and green protons trans to each other. The medium coupling constant is 10 Hz and corresponds to the coupling between the orange and red protons with a cis arrangement. Finally, the smallest coupling constant is 4 Hz and must be between the red and green geminal protons. Sometimes knowing the coupling constants is just enough for the accurate assignment of most of the protons in an organic molecule. As a rule, assignments based on coupling are more reliable than those based on chemical shift alone. Ethyl vinyl ether is a reagent used for the protection of alcohols. All its coupling constants are smaller than those for usual alkene because of the electronegativity of the oxygen atom, which is now joined directly to the double bond. It is still a simple matter to assign the protons of the vinyl group as couplings of 13, 7, and 2 Hz must be for trans, cis, and geminal protons, respectively. In addition, the proton underlined in orange is on a carbon atom next to oxygen and so goes downfield, while the red and green protons have extra shielding from the conjugation of the oxygen lone pairs. Geminal coupling on saturated carbons can be seen only if the hydrogens of a CH2 group are different. The bridging CH2 group of mertanol, described earlier, is a good example of geminal coupling on a saturated carbon. The coupling constant for the protons on the bridge is 9 Hz. Obviously, geminal coupling constants in a saturated system can be much larger than in an unsaturated one. To sum it up, in the last 2 lectures, we examined the main types of couplings in proton NMR spectroscopy. You saw that couplings between neighboring hydrogen atoms are affected by the bond distance between the protons, the angle between the 2 CH bonds, and the presence of electronegative substituents. Coupling is possible even for hydrogen atoms connected to the same carbon, as long as the system is not symmetric and the geminal hydrogen atoms are different. The most common coupling is between vicinal protons. In this case, the smallest values for the vicinal coupling are seen for saturated systems, and the coupling constants increase for unsaturated systems as the distance between the vicinal protons shortens. The largest coupling constants are observed for transalkenes, as the coupling occurs through the bonds, and the more effective parallel alignment of the bonds in the trans compound provides better communication between the nuclei. Coupling between more distant hydrogen nuclei is rare but can be seen in allylic systems and metaprotons in aromatic systems. Long-range coupling is typically small and does not exceed 3 Hz. You have now been introduced to all of the most important spectroscopic techniques available for determining the structure of organic molecules. Hopefully, you can now appreciate why proton NMR is by far the most powerful of these techniques, and I hope you will refer back to this module as you progress through the rest of the course in organic chemistry. We will discuss proton NMR extensively, and specifically, I will revisit it in detail in a later module where we will explore the use of all spectroscopic techniques in combination for more complex systems. Thank you for your attention and participation.